Okay, today's lesson is a control system evaluation. Now we will evaluate the difference of control in system. The control system must be balanced the energy gained by the process against the energy lost by the process. So this means that when we are running as a control system, essentially you control the motor system. So supply is taking the supply energy. In the meantime, when the motor is circulating, so this means that motor will consume more energy. Sometimes it will dissipate more energy. So in this case, to maintain a stable control system, so energy gained by the process needs to be balanced by the energy lost by the process. So this is the way you use the control that evaluate the control system. A control system must balance the energy gained by the process against the energy lost by the process in order to maintain the desired value of the control variable. So this is important for the control system. So when you are making a control system, so load can be changed. So when the load change, so in this case, the error can happen. So in this case, control system need to minimize the maximum value of the error and minimize the settling time and minimize the residual error. When the error is happen, so this error needs to be settled in a very small time. And also, once the error has been settled, that time sometimes can happen with the residual effect. Residual effect means when you are making a damping system, this vibration or oscillation happen, those has to be eliminated. So those control systems need to do characteristics. As the maximum value of the error, minimize the settling time and minimize the residual error. So when you have this is a load quality here, the load can be changed. Load can be changed that we done a set change in the load. So when I set change in load, this is horizontal with the time. So that way the set change in load, so that way this way the vibration and damping happen. So this is for the damping happen. This is for the time. So this we done as a control variable. So this we done as a time. So this is a control happening. So this figure when a section happen, so this will be a variable happen. So this variable needs to be the minimized. Okay, so this is the changing happen like this. So this is the really unstable and finally will be stable. So in this case, this unstable region should be the minimized. And in the short time, unstable region should be minimized. For example, this is for the resistor. Process you can represent by the resistor and the capacitor. So this is the process. So this is the capacitor C. So in this case, there will be a resistance 7. So this is horizontal AC with the time. And vertical AC means the voltage. Voltage for the capacitor, so we can draw a reaching cut like this. So this is the EC and the time cut. So this guy is you can put this one and this one are similar principles. When you are filling the water, so this is filling the water into the water tank. So this is a water tank or water filling. The water will get going up. So when the time is increasing, so water has also be the water level also be increasing. So this is for the similar principle. So this electrical capacitor and the electrical can use similar to this water level. So water level going up, so this one will use water level will be also the higher. So this is for the process system. So similarly, you can also see the pressure level here. So this is for the supply. So this is the supply. So this supply, so this is all you can see the supply. Supply will be increasing, so this pressure also be increasing. So this is the pressure. So this is the tie. So when you tie increase, the gas pressure will increase. So this is also can draw the similar diagram. Processor system. So this process system this is tie capacitor. This is a capacitor means that when you get the most charging to get capacitor, charge will also be voltage also will increase. And this line is similar to the water. When you fill the water to the tank to the water, so for the time is going on, the water level will be increasing. And similar to the time and the pressure. So when the time is going on, the pressure level will be higher. So this is for the voltage, capacitor voltage, and the water level and the time can be drawn by this diagram. So what the heat here? So this is heat. And then you get the temperature. So this is thermometer. So the pressure hit the tie, the temperature will be higher. So this is for the heat and the temperature. So that we can see that electricity and the water pressure and the tie, these are the similar characteristics. What is the process capacity and the capacitance? When we are use the process capacity, for example, for the air tank, or air before the air is tank totally empty, you can easily put the air into the tank. Once the air tank is about to full, so the compressor will face the resistance. So this is the way. And similarly for the car, if you drive the car, if car is not fully loaded, so you easily move the car. But when the car is very heavy loaded, so it's difficult to start the car. So these things are process capacity and the systems are depending on. So when the capacity is higher or the loads are higher, in this case, it is difficult to make a change. So this is why in the control system, we use the flywheel control system. When the generator is started with the flywheel mover, so and these are changing on the vibration, we change the generator speed. So the choose that minimize the generator speed, we have to utilize the flywheel. So flywheel is a heavy wheel rotating, so the by taking exception the flywheel, we just maintain the constant speed level. So this is the way that we have to maintain the speed ability. When the system change happens, so that the change are the vibrating, so that those damages we can use to minimize the damage. So this is the this is for the system here. So this is the low change. Low change with the string with the vibrating with the going down like this. So this is for the damage. So this is damage, this portion with the overshoot. So the damage is happens, so this will be the overturn system. So this is the overturn. Overturn means that when the system reaches the final value quickly, and this one changing the vibration too much. So this is the overturn. So another way is the underturn system. Underturn system means that this system will not reach the final value very slowly. That will reach the final value. So this is the underturn. So both the overturn and the underturn are undesirable. So in this case, we have to minimize the damage. So in this case, we have to utilize the critical damping. Critical damping means that when you increase the damping, so then we can damping should be like this. So that is the critical damping. Overturn, underturn, and the critical damping are important in the control system. This is we use for the position control, position 1 and 2 position control. So the 2 position control is used for the process control is not required. Process has a large capacity and the energy inflow is relatively small compared to the energy within the process. So in this case, we use for the 2 position control. Especially the 2 position control can be the level control and also the differential gap control. So this is that we can make the 2 control process. One is the level control. And another one is the differential gap process. Differential gap control. So level control and the differential gap control. The position control can be the two position is the relatively small unit of energy in the process. So this is the two things. And that's our differential gap control system. We use that make that our control. So firstly we draw the level control diagram. So this is what in this case this is the water bar. So this is water bar we control. And this one is the floating switch. So this is the floating switch system. So this floating system we use an on-off control. With this on-off control, we make the gate controller. So this is the water control system. So in this case, water control system, how we control system? This is for the tank level. So this is we put a stepwise. So this is for the tank level. So tank level, so water controller is when the level is small, in this case water controller, or when it is high, water controller will be off. And level is low, water controller will be on, off, or off like this. So the whole of the data you can see that this level, the development level water controller on and off. So this kind of control. So this part of the level control system. So this control system is a two position control. Only use the on and off control. On and off control is utilized. In this case, precise control is not required. Precise control means that sometimes very smoothly you need to change the level. But this one is the on and off. So when the on, this one water will flow inside, but off this one not flow at all. So this is kind of system we cannot use for the very precise control system. So level control, we use as an on-off control system. Another way is so this is where the open and close only thing can happen. So this is the on-off control system utilized for the level control. So another way is that different gate control means that controller got the upper and the lower limit. So this is the different gate control. So this becomes the upper limit and the lower limit. So upper and lower limit can happen. So in this case, upper and lower limit is that this is the open and the close. So open and close are dealt with the two level. So this is the open and the close are just two levels. Upper and the lower limit, so this is the level. So the upper and lower limits are depending on the change difference between the upper and lower limits. So those are controllers are working. So this is for the controller the level. This is the differential control system. So this is why in the diagram we can store it here. So this is the stepwise. So stepwise. So that will be like this. This will be a stepwise, so this is for the upper limit. So this will be the lower limit. So upper limit and lower limits are we make the control. So there will be on and off control here. So there will be on control. So this is the off. Off control means this is for the control here. This is the on-off control system. So step one and on-off control, we use as an upper and a lower limit. So when this limit is too large in this case, we make it as a controller. So that level control and the differential controls are utilized for the process is not required, process control is not required, process is a large capacity. So we don't need a too much GD control, precise control is not required. So we can utilize the on-off control and the differential gap control system. If you need a system very accurate and a very precise control, in this case you have to utilize a provisional control system. The provisional control needs to be utilized for the precise control system, and the derivative control needs to be utilized for the any change need to be controlled, and individual control system needs to be applied to eliminate the error. So those control systems are very precise control. So I also give that control system. inside control system, we use for proportional control. This is the proportional control. So proportional control provides the correction proportional to the size and magnitude of the error. So there are more errors, so there will be more control actions applied. So this is the we use for the proportional control system. So this proportional control system we call it control. So this is the input and this is the reference. So this is the process. The process control that utilizes the bar. So this is for output. So detail on the input and the reference between the difference between the input and the reference function. So we provide the control function. So because of this one, this proportional control means proportional control the amount of power delivered to the process, and this will reduce as the error is reduced. So this is the proportional control. This is the proportional control. So when the normally the input function make a comparison with the reference, and this reference will control the process. So this is the proportional control system. The proportional control the amount of power delivered to the process, and this will reduce as the error is reduced. So in this case, we can write the equation. So this is the gain. Gain means the change in the output, and the ratio between the change in the output divided by change in the input. So this is for we can write the equation that gain. So in this case, output is equal to error multiplied the controller gain. So this equation. So output equal to the error multiplied controller gain. So this is for the output. Output is equal to the error multiplied controller gain. Controller gain is that. So in this case, this one we can replicate. So this is for the operational amplifier. So we draw the proportional control diagram. So this is the diagram for the proportional control. So that will be the input will be V1 into R1. So this is the positive. So this will be this is the R2, and also will be the V2. So this will be the negative. So this is the proportional control. So when the V1 is an input, so then we can adjust the R1, R2 to adjust the output. So the proportional gain can be adjusted. Then to adjust the R2 or the band, you can adjust. Proportional control we can calculate. So up to this year, we're talking about the control system. When we are making the control system need to be very short line need to be set there. So any change happens, so this controller will vibrating. So vibrating means the unstable region. This unstable region need to be minimized. After the sound oscillation happens, the vibrations will be stable. So in this case, our controller characteristic is it needs to minimize the maximum value of the error, minimize the settling time, and minimize the residual error. So when we are making the process control system, so then we do the process control when the time increase and the process voltage also increase. So this is for the voltage system and the water system. When the time going on the water level, and then when time going on pressure increasing, when time goes this thermometer, temperature will be increasing. So those are the process control system. So we have to utilize the process control system as a very similar characteristic. So when the control system happens, so there are reviews over them, under them, and the critical them. So as soon as the switch off, this is the controller, the value reach to the maximum value, and they are vibrating, so then we use the over them. And it takes a long time to reach the final value under them. Critical them means the appropriate time it should reach the final value and should be set there in a short time. So this will use the damping system. So the those characteristics are required for the controller. So the when we are controlling the system, there are the basic control is that two position control, position on off it, on position 1 of the position 2. So for the water flow level 3, when the water level low, this is on, and then the bright water, water level 4, off, and then the flow water. So this is only the control we use the on-off control. So this also sunlight controller means this is open and closed level between two levels. Upper and lower limit the controller is working. So this is the level control and temperature gauge control. Those controls are utilized for the not too much of precise system. If you want a precise control system, in this case, when you utilize the provisional control. So the provisional control provides the provisional to the size and magnitude of the error. The provisional control, the amount of the power delivered to the process, and this will reduce as the error is reduced. So this means that we can write the equation. K is equal to a change in the output divided by change in input, and the output is equal to error multiplied by the controller gain. So that this controller gain you can adjust. By adjusting the resistor R2, you can adjust the gain. So that gives us a differentiator operational amplifier. So we use the operational amplifier control system for the operational control. So in this case, we use the force in the weak light. In the percentage group. We can calculate K, so K is 100 divided by percentage dV, so 100 divided by 6.67 equal to 1/5. And similarly, so if the K is at 0.75, you can calculate percentage dV. So percentage dV is 100 divided by 0.75, so equal to 133. So this is the relation between K and the percentage proportional band. Reset system. Reset means that when you are making something here, the control is working and this control reset overflow or something, and this you can reset. Reset means that in a motor system, sometimes your motor is run other than for example, you see the circuit breaker. Circuit breaker system when the electrical current high to circuit breaker will cut off. So other than you need to reset. So you have to manually reset the circuit breaker so the circuit breaker can work again on the next time. So this is integrate proportional integrate control means that it can automatically reset. When the system is happening, the control happens, then this one system, the controls are for the temperature or the pressure are very high. In this case, the controller operate and then cut out the system. And when the temperature, the pressure will fall down, so this should be the reset. So the integrated proportional control function not only that provide the control but also provide the reset function. So this is the basic principle of the integrated and the proportional control and the integrated control system. So integrated control is especially the reset. Reset means we don't use the reset itself. We have to utilize with the other control function, especially the proportional control. When the proportion is too high, in this case, control function make the performance, and then the reset function make the reset again to the original position. So this is integrated control is rarely used by itself, is used with the provisional control. So integrated control is also known as a reset. So integrated action provides a correction proportional to the magnitude and the time duration of the error. So the integrated action eliminates the offset due to the load changes, which will order with the provisional control. So in this case, we can draw the electrical diagram. So electrically, we can draw the integrated and the proportional control. Normally, the proportional control, you can draw the electrical diagram. So there are two resistors for the operational amplifier. So that this feeder resistor R2, forward resistor R2 provide the gain. And similarly, we can utilize for the integrated control system. Instead of the resistor R2, we can put the capacitor. So in time, then you can change the integrated control. Instead of the resistor R2, we provide the R2 and the capacitor C series so that it will be the proportional and the integrated control. So that in this case, the control system you can see this diagram. So this is the only thing difference R1 is connected to the positive. But for the integrate and the proportional control system, we have to change the sign. So this hour is need to be connected to the negative. So I give you the diagram for the integrate and the proportional control. Integrate control diagram and the integrate plus the proportional control are combination diagram. So integrate control diagram. So we put the capacitor C1 between the negative terminal and the output terminal B2, so that will be that we can get the integrate control. So, and then the R2 and the C1 in series between the negative terminal of the operational amplifier and the output terminal, so we can construct the proportional plus the integrate control system. So this means that proportional control and the integrate control we can utilize for the position. So in this case, this is the input integrate side. So in this case, adjustment. We have to change the adjustment. So we can change the integrate side or the repeat per second. By this way, we can use the calibration. At time I means the time taken for the integrate action to repeat the change due to the proportional action. So this is the integrate side. So in this case, we can see that input function. So input will be changed. So this is a set change. So in this case, output will be changing like this. So input change, output will be changing like this. So now we can calculate the formula. They are the effects. So let's say now the integrate effect is a minimum change of the size. So that we can calculate the total change in the output. The equation is total change in output. The total change in output is equal to change due to proportional plus change due to the integrate proportion. Change due to proportional plus change due to integrate proportion. So this is the total change in the output. So total change in the output can be calculated. The change due to the proportional plus the change due to the integrate proportion. So by this way you can calculate for that the change equation. Now make the comparison. So the speed and the size are characteristic. So there will be the open loop control, proportional control, slow integrate, and the faster integrate happen. So in this case, this is you see that this is the time curve, and this is the speed. So motor is running, so without no load, the speed will be this speed. So this is a no load speed. Okay, so this is no load speed we running, and when the no load speed running, that time we can supply the load. So this is a no load. So no load speed. So no load speed, I showed that this is total line. So this is no load speed, and then we put the load. So this is the load off. So because the loading effect, how the motor will be performing. So motor sunlight can perform like this. We change it along the normalize. So that will be this control by here the first integrate. And sometimes we can also see that when as soon as you put the load, motor speed will go down, and then this one will go back to the normal. So that will be slow integrate. Another one will be the control system. When you are put the load, so load you use the load for the long time, so sometimes motor speed will be going down. So this is for the proportional. So when you put the load, depending on the load value, and the motor speed will be go down. So this is the proportional control. So without providing any control, the motor speed will be go down the way the more. So they will open the control. So this is depending on the sky or the load. So there is if you provide with the fast integrate control, the motor speed will be go back to the normal. So there are variations, oscillations, and go back to normal. But it's a slow integral control. It will take a longer time to reach step back to the normal. The proportional control means that the more the load you put, the more the slow down the motor. So open loop control means that without providing the any control machine, when you put the more load, so motor speed going down will move the speed up. So this is the comparison between the kind of integral control, open loop control, and the proportional control. So those kind of the controls systems are utilized in the industry, especially to control the motor. So in this case, delivery control machines we can use based on the rate of change of the error. For proportional control machine, depending on the magnitude of the error. So depending on the magnitude of error, this will be the proportional control. Depending on the rate of change of the error, it will be the delivery control. So in this case, the delivery control, we have to examine how much change happens. The rate of the change needs to be examined. So in this case, in the rate of change means that this is a differential. Derivative means the rate of the change. So depending on the rate of the change, the control machine operating. So this is a derivative control system. So normally we can utilize the proportional and derivative control altogether because when the magnitude of the change happens, so the control machine is a proportional control, and depending on the rate of the change, control machine provided, so it will be a derivative control. So derivative control is a provided correction that are proportional to rate of change of the error. To speak as a response time, when the derivative rate of change is faster, the response time will also be the control response time will also be the faster. So this is the detail of the tool. When the rate of change is slower, the control response time will also be slower. And also it also provides elevated overshoot. So overshoot can also be reduced by the proportional plus a derivative control system. So control diagram. So the diagram for the proportional and the derivative control. So electrical circuit diagram. So this becomes a proportional derivative control or the PD control system. So this starting with this is the V1 input. So this way this is R3 and this is R1 connected in parallel. So in this case R3 is connected in series with the capacitor C2 and is connected with the parameter R1 and they are connected to the operational amplifier negative side and negative terminal, and this is the R2 is connected between the negative terminal and the output terminal. So output voltage is the V2. So this will be the positive is a distance connected ground. So proportional plus derivative controls circuit diagram. So off and circuit showing the P plus D is a control. Off and circuit showing P plus D control. So this is for the proportional and the derivative control system. So let's get diagram. So in this case, this is for the only R2. So this function will be the proportional and the derivative control. The proportional control and derivative control we get this one. So in this case, the controls are variable changing like this. In this case, almost the derivative control we also provide like this. So this becomes a TV. So the derivative side. This is the derivative side. So this means that when there's an input is changed, so that will be the output will also be changed. So the changes and the initial SOSs are dispensed change by change. So this means that the derivative time change happens. So this derivative time flow we can draw to backward and this is lead at this point. So the difference between the horizontal cutting point and the point where the derivative control again starts, so that will be the PD. So this is 50 means the derivative side. So this is a control diagram for the derivative side. So the derivative operational proportional derivative control we can represent by the electrical diagram. So that will be the operational amplifier. So R3 in series with the C2 and then paired with the R1, and then they are connected to the negative side, terminal of the op amp. So then the R2 is connected across the negative of the operational amplifier and the output P2. So that will be the proportional and the derivative controls are electrical diagram. So we also utilize for this function is only with the sense derivative control. Derivative control means rate of the change and proportional means the magnitude of the change. They are sense and the control function provide the control action. But it does not have the any reset. So reset means integrate. So in this case, if you want to put the reset, you also need to combine with the integrate control. So integrate is represented by the capacitor. So the R2, if you connect the R2 in series with the capacitor, so your control system will be a proportional plus integrate plus derivative control system. Now I give you the diagram for this is the PID. PID means the P means the proportional, I mean the integrate, and D means the derivative. So I will give you the diagram. The control system is utilized. So this used on the process where the sudden change or the sudden change of the low occurs and one or two more the control is not the capability of the keeping the error within the acceptable limit. So this is the way why we need to utilize for the PID control system. Because proportional control is used for the stability, integrated control is make the reset so to the element the offset, derivative control is the direct. So especially the controller, as well as the input change too high, in this case the controller response needs to be fast. So controller response needs depending on the rate of the change of the error. So error changing is too high, in this case controller should be the faster response. So to make the faster response, derivative control is provided. To make the offset means that go back to the normal system. So in this case, we have to utilize the integrated control. And to provide the appropriate proportional control function, we have to utilize for the proportional control. So the answer for those control functions are utilized in the electric industrial system. So to provide the proportional, to provide the offset, to provide the overcome the dialect. So now I give you the controls are typical diagram. Diagram for the open loop control system. So this is the open loop control. So this is for the open loop control means that this is usually the potentiometer. So this is the potentiometer. The potentiometer this is for the this 5. So this is the 0 volt. This is the 10 kilo ohm. So in this case, this Vin is a supply to the operational amplifier. So this is a drive amplifier. So this drive amplifier output is connected to the motor. So this is the proportional open control. Open control means that it does not provide any feedback. So only depending on the input voltage, the motor will be running. So this is the open control system. Okay, so this open control system, we have to utilize the closed loop speed control. In this case, the proportional control we have to utilize. The closed loop speed control. So this is the proportional control. The closed loop speed control or proportional control. In this case, we provide the proportional control means that this is for the potentiometer. So this is a positive 12 volt. So this way stepwise. So stepwise, so we put the resistor here. So those are resistor. We connect it. Then this is connected to the negative and the positive terminal. So then this here we have to utilize for the gain. The gain means that this is for the gain. So this is the 0 volt. So this potentiometer, this function, this is for the proportional control, and then this one is connected to the Vin or the output drive amplifier, and this drive the motor. So motor is coupled with the tachometer. So this tachometer is coming out is a V out. So this tachometer voltage is feed to here. So this is for the proportional control system. So this is the diagram of proportional control. When the error change happens, so this way means the proportional control system is working. Another one will be the integrated control system. So it does not have any reset function. So if you want to put the reset function, you have to use the integrated control. So closed loop speed control and integrated control. Closed loop speed control, so integrated control. So for the integrated control system, so to make the integrated control, here you have to put the capacitor. You need a capacitor. So in this case, you have to put the two set limit. So this is the set limit here. So this is plus 12 volt. So this is a 0. And resistor here. And another one with the plus 12 volt. So this is 0 volt. So this is for the step 1. So this is step 1. Okay, this is for the you put here. So this is that we remove the capacitor. So 1 microfarad is connected. And then this is connected to the negative and the positive terminal. So this is connected to the drive amplifier. So this is a VIN. So this drive amplifier drives the motor. The motor is connected with the tachometer. This tachometer is coming out with the VR. So this VR is connected to pressure here. So this is resistor, so we can pull like it. So then we just so this connection we just step. So this connection we use the integrated control system. So integrated control system, you have to put the two step point. So one for the provisional control, and this is another step point. So by this way you can make the reset action. So we put all the capacitor here for the integrated control. So in this case, when you are making the reset the circuit, output to 0 volt, show out the feedback capacitor. So in this resetting can happen. So to reset the circuit, so put the output to 0 volt and show out the feedback capacitor momentarily. So this is for the reset function. So I am talking about the open loop control, closed loop proportional control, and closed loop integrated control. So integrated function to make the resetting. So reset function is provided to reset the circuit, put the output to 0 volt and show out the reset capacitor momentarily. So then we can call it the integrated control system. I also give you the two more diagrams. Proportional and the integrated control system. So this control is only the integrated control. So that we also need to draw a circuit diagram of closed loop speed control, proportional and integrated control. So I give you the circuit diagram for the proportional and integrated control. So proportional and integrated control means that not only that provide the proportional control, but also that provide the reset function. So the reset function and the proportional control function are provided. So this is the proportional and integrated control. And the integrated control function. So proportional control we provided this one set is a step 1. So this is for the proportional control. So this portion will use the proportional control. And this is the capacitor, this is the K, another potentiometer. So another potentiometer and the capacitor circuit is provided integrated control. So this means that not only provide the proportional control function, but also provide the reset function. So this is for the proportional and the integrated control function. So the next one we use our proportional plus a derivative control function. So we can utilize the proportional plus a derivative control. Proportional control is when there's a change happens, so control function is provided. And derivative control means the rate of the change. So in this case we use the differentiator circuit. So that this so depending on the input, the change, the speed of the change, the speed of the response, depending on the rate of the change. So the final rate of change the higher, so the control speed will also be higher. So by this way you can provide the control function. So control speed will be faster when the rate of change will be higher. So this function can be provided by the proportional plus a derivative control. Now I give you the circuit diagram for proportional plus derivative control. Those are the controllers are the basic principle. So that way we provide a proportional control, derivative control, open group control, closed group control, and proportional plus derivative control, proportional integral control. Those controllers are we provide. So that both controllers are this is for the diagram here, and also you put that control loops are conditioning. Control loop conditioning. So those control loop functions are we can integrate through the predicate system. So normally we use the transducer. The transducer is you use the converter. So this is a here we use for the controller. So this controller we include the two kind of control system. So this controller block the Bosa module we include the closed loop speed control, proportional, integrated, derivative control. Those modules are for inside. So this is controller. So normally this controller is we can utilize for the analog to the digital analog system. So normally input signal we use the analog, so we use the ADC, analog to digital conversion. So in the before this lesson I already given you the signal conversion, analog digital analog conversion step. So those systems we use we change the digital signal, and this control system operate and they change back to the analog signal. So that we use the ADC and DAC in the controller. And after this analog output control is change to the converter. And then this is connected to the SCE. SCE is the final control element. So SCE will include the output switch, output relay, those things are we included. So this is for the output final control element. So in this case, we utilize for the control system. So we also utilize for the PLC system. So in this case, since the final control element may include the PLC here, so then we use the digital signal input. Digital input. And this we use the PLC. PLC means the digital line. So then this PLC utilize the DAC. DAC will change the output analog signal. So this is the analog output. So the analog output is connected to the motor. So this is the motor. We can also utilize for the microprocessor controller. So controller microprocessor. Then you can use the digital to analog converter. And then you can use the pressure converter. IP. IP means the current is the pressure. Current to pressure converter. So that's how you use the automatic control bar. Pneumatic control bar. So those are the typical control diagram. So we use the controller signal conditioning so that now in the controller module we include the proportional PID control, integral control, derivative control. Those are included in this module. So normally the input speed or the temperature is sensed by the transducer and converted to the digital. So the loop controller make the control, and the final is coming out as a digital. So we converted to analog, and converter is fed to the final control element. So if you are using a PLC system, then we use the digital input line. So the PLCs are changed to the DAC, digital analog conversion, and analog control the motor. Either you can also use a microprocessor control. So in this case, you also outboard the microprocessor is interface with the DAC. DAC means the digital to analog conversion. Then so we set to the current to the pressure converter, and we provide the control for the pneumatic bar control. So this is for the pneumatic bar control utilized for the industrial pressure control system. So those are the control loops conditioning. So this is for the typical control loop conditioning diagram. It's a utilized in the industry. Sometimes synchronized control is also utilized. So So the input function and output function need to be synchronized. And also we also utilize what is our data transfer. Data transfer means the wires are connected to the controller to the process. So in this case, we also need to use that communications system. So I also give you the electronic signal system, so the communication system aspect also we utilize. So those are the control functions are related to the control and digital analog conversion, signal conditioning, communication. So these are integrated in this control aspect. It is a control line. So normally we use for the transmitter and receiver, we use a multiplexer system. So instead of that we are using the server line, we use a single line, and we use a multiplexer. So multiplexer is provided at the both transmitter and the receiver section. So by this way you can reduce the amount of the wire requirement. So in this case, they are the this control, typical control is channel 1, 2, 3 that is the control function. So in that way, they are the for the digital station. In this case, we need to send the digital speed, temperature, low, everything is control function. Those control functions are utilized for the data system. So that way, this system we use a sampler. We use a sampler. So our sampler is fast amplitude modulated signal, PAM signal. So these PAM signals are the analog. So that when you are one the thing, so we have to provide it to the digital. So in this case, we have to use the encoder. So that those signals are analog signals are changed to the PCM. PCM means the fast code modulation signal. So those signals are fed to the controller. The controller then make the calculation and set out the PCM signal. And then we use the decoder and the change to the PAM signal. And after that, this sampler change to the server channel. So that by this way, we can send the signal, we process the signal, and then we transfer the signal. So the industrial signal system, we use it as a transmitter and as a receiver and a multiplexer utilized. So for the most accurate control, we use it as a sampler system, encoder, and a PCM system. So those are the signal conditioning system. So sometimes we also need to connect the filter. So sometimes a control is beyond the starting limit. In this case, you have to utilize the band pass and the band source filter. Are also required to eliminate any harmonic or any undesirable frequency. Band pass and the band source filter system. Band pass system means the starting frequency band needs to be passed. So this is the connection of band pass filter. And this is the connection of band source filter. So starting frequency band and undesirable need to be stopped. So that those band pass and the band source system are also utilized for the control function. So only the starting control frequency range need to be utilized. And sometimes the starting frequencies are undesirable need to be stopped. So that we use the band pass and band source filter in the control function. In the meantime, we use for the multiplexer, encoder, decoder system to transmit the control signal. So what is the best process? Especially the manufacturers produce their production in the batch. Batch means that when we are making the production system, normally there's this one machine process. They cut off the one machine's production, so they produce the starting amount of the material, so product, so that those are one step all output coming out, those outputs are the process by another step. So batch by batch production. That's why batch production is for example, you want to produce the 1,000 items. We don't produce the 1,000 items continuously. Firstly, we produce the 100, and then this 100 we process everything, and then another 100 will process. So this is the batch by batch process. So batch process is utilized. So in this case, utilize the batch process. So in industries, we also need to control the batch process control diagram. So batch process control diagrams are typical control diagram. You need to draw the typical control diagram for the batch process. Okay, I say and I draw the diagram. Batch process system. So the batch process manufacturer is a product in a batch. So it has been a discrete amount. Rather than a quantity, the required ingredients are fed into the process vessel in the required amount and in right sequence. The vessel is then heated and pressurized in appropriate sequence. In an appropriate sequence. in order to produce a desired product. So in this case, we have to make a sequence control system. Sequence control, so we have to put the setting and the sequence control and the rotating and the pressurizing, heating, those things have to be utilized. So in this case, we have to utilize for the appropriate sequence control and appropriate PLC system. So PLC means that we are switching to the appropriate sequence control switching to be provided. So I give you the circuit diagram of that one. Typically, we have a process system. So input liquid. So we put the input liquids that they so the opening bar. So those bars are controlled by the PLC system. So they open and put as a bar. So for the liquid is input, and so appropriate amount of liquid B input, liquid C input, so they put. So in this case, we are using this TD and LD for this is the field flow. So this is connected to the analog and the sequential controller. They are connected to the analog and the sequential control. So after this, liquids are there, they put. So this is the motor, we make the steering. So motor rotate and they mix the thing. So this is the motor. After they making the steering, so after the sequence happens, steering sequence happens, then we do the heating. So this is the heating part operated. So there is the BSC system provide the heating. After heating finished, so it can provide the steam. So those steam need to be the discharge. So temperature maintained. So and then the steam is flowing out, and after that this out, there is stop it, and those output liquids are discharged. So this is the typical process. So those processes are normally connected by the controller bar. The controller off the switch, magnetic switch. So magnetic switch are operated by the PLC system. So this is the typical control system. This is for the batch control system. So this batch control system is a batch by batch. Liquids are free and motor start steering and heating and temperature maintained, heating station off, failure off, and the part of the liquid. And then repeat again this step. So this is for the batch control. Sometimes the batch control and the continuous control also need to be combined. So I will give you another diagram for the batch plus continuous control. For both the continuous control and the batch control. So this is in a continuously. So this is for the batch and the continuous control system. So we have these answer the things input terminal. Input terminal means this is the input terminal. So process the wire. For the process we can connect the wire. So this is for the input terminal. So input terminals are A4 and A5. So identify the input terminal. So this is the A4 and the A5. So this is A4 terminal. So this is A4, here A5, A4, A5. So this is the input terminal. And also identify the output terminal. So output terminals are coming out. So this is you see the thing. So this is A7. So this is A7 and A8 are by the output. So output terminals are the A7 and A8. A7 and A8. The C, controller function block. So which one is the controller function block? So in this case, this controller function block are the FE13. So this is FE13. So this is the main controller. FE13s are the main controller. PID, so proportional, integer, and derivative control. So this is the FE13. Now D. These are auto manual functions. So AM. AM means auto manual function. So auto manual function is a FE14. A means auto, M means manual. So auto manual is AM. So this is the FE14. So this is a function block. So we can change the auto and manual by the FE14. And then, so this is the FE14. This is the auto and manual block. And then it's suppose the P and the B. P means the display. So P the process variable, and P is the PI is you can see the P. P is the process variable. Process is a variable process. B means control to the bar. So P means process variable. And the B. So B means output signal to VAR. Output signal to VAR. So these are, and then the F. So F is after the identify the stepwise function block. So stepwise function block is we need to set the function. So here, this is the FB17. Every 17 we set the function. Every 17 is a stepwise. Stepwise means when the temperature or the pressure is here, we need to set the starting function at the FB17 point. So this is our stepwise. So this is similar to the reference. So in this case, here you see a stepwise function block. So that will be the FB17. And then G. The difference between loop 1 and loop 2. So loop 1 has, as you can see, the loop 1. So in the this 2 diagram, so 2 loops. So this is loop 1 means tracking stepwise. Control line menu where we can put a stepwise function. So the loop 1 has tracking stepwise. So you can see that this one here is this loop. This loop is that you can see this loop. So this is a tracking stepwise. And this is loop 1. Loop 1 is this one. This one and then this one loop 1. So they call it a tracking stepwise. So tracking stepwise, we put a tracking stepwise and then we can, so any level change you can make it a stepwise. So this is for the loop 1. And loop 2 is that does not have a stepwise. Loop 2 is that this one is loop 2. Loop 1 for the stepwise, loop 2 does not have the stepwise. The most important one is that this stepwise you can move the chain you have to move the tracking stepwise. Tracking stepwise means that when the output change, they can make the feedback. But this one is stepwise is on it. So the stepwise does not depending on the system value. So this is this diagram explains that this is you understanding the interpretation of the control function. So which is the input, which is the output, which one is the auto manual, which one is the stepwise, which one is the process, which one is the bar. Those things you can understand by clearly the this diagram. And now summarize. So the two days I teach about the most explanation about the control function. So we utilize the control functions as signal conditioning. So requirement of the control function, and the proportional control, individual control, driven control, and the utilization with the motor. Those I explained. And then I use the overview diagram of the process control system. And the interpretation of controller loop. So this is the two-day function. So in the control functions we also utilize the process control system, PLC control, switching on off process. In the meantime, the controller characteristic is also important. So the control function is normally that we change the temperature and pressure to the electrical. So the electrical quantity need to be changed.